could you outline for our listeners the kinds of practical things that we can do to take these very large language models and have them be useful in real time in production for, say, a user of a platform that has an LLM running in the background?
Yeah, sure. I would say also that the kind of techniques I mentioned, they often depend very much on the use case and also the size of the model. So there are things that kind of work okay for smallish models, but then they just don't really apply at larger scales. And in the book, we kind of cover, I would say, three main topics or areas. One is called knowledge distillation. And this is an old idea, it goes back to Jeff Hinton and others before him, where the idea is that you've got a capable model. So this might be something that is like, let's call it the teacher. And this model is too big to deploy efficiently. Maybe you want to deploy something on the edge or, in a cheaper way. And so this knowledge distillation technique allows you to basically take essentially information from this teacher model and kind of imbue it in a much smaller, more efficient model. And when it works, you typically get comparable performance. You take a small amount of a hit in your, say, accuracy. But often the trade-off is worth it because, in real life situations, accuracy isn't just the only metric. You're worried about latency, you're worried about cost and things like that. So this works quite well for models in the sort of 100 million parameter range. So things like BERT, it works well. For small GPT models, it works okay. But no one has kind of figured out how to crack this effectively at the very large scales of tens of billions of parameters. And that's why, for example, we haven't yet seen, as far as I know, something analogous to distill Llama 65B or something like that. So that will often get you roughly maybe a 2x reduction in latency. You can usually compress your model about half. And then there are other techniques which we discussed. So the most common one that's used for many use cases is called quantization. And the basic idea here is to take the precision of the weights that the model was trained in and just cast them to a lower precision. So typically things like 8-bit or 4-bit is now the sort of new standard. And this then, because you've now got lower bits, you can basically, do your map mols or matrix multiplications faster and use less memory. And we can talk. There are a bunch of different quantization strategies we can talk about, but the sort of other element we mentioned is this idea of pruning. So here, the basic idea is how can you kind of delete weights in the network altogether, but still preserve the sort of overall performance of the model. And when we wrote the book, the sort of current state of the art was a technique developed at Hugging Face called movement pruning, where you basically, it's a pruning technique designed specifically for fine-tuning transformers. But all of the kind of hardware that sort of like the sort of consumer hardware that existed basically didn't really help you, because even though you delete all these weights, you need to save them as sparse matrices. And then these sparse matrices, they don't really get any bit boost on like standard, Intel hardware. So we kind of concluded that pruning at the time wasn't quite mature enough to be used in production. But my colleagues at Intel have said that they've now got some quite impressive approaches where you do get genuine sparsity and fast latency. So those are the three main techniques, and we can kind of dive deeper if you want.
Yeah. Model distillation, quantization, pruning. These are the three that come to mind for me as well in terms of production deployments. Great examples that you gave there, and cool to have you break down for us so clearly the kinds of circumstances where one of these approaches might work well versus another. I think I will actually leave that topic there and not dig too much deeper, because there's still so many more things that I want to
Sure.
get into while we're recording.
But maybe I could mention one thing
Yeah.
specifically about like generative models. So
Mm-hmm.
These like kind of techniques I mentioned, they're very like kind of generic, and you can usually apply them whether it's an encoder or decoder, it doesn't really matter.
Mm-hmm.
But one of the big bottlenecks when you're doing chatbots is having a fast response, right? So if I ask a question like, what's the weather like today? I don't want to wait a minute to get my, text back. And there's been a lot of cool innovation around streaming tokens. So this idea of like sending the user like kind of like, bit by bit the answer. And that's what you see in ChatGPT, right? Like you don't have to wait and then get the full answer. You can see the answer being kind of generated on the fly. And one of my colleagues at Hugging Face called Olivier, he built this very, very cool server called Text Generation Inference, which not only does this token streaming, but it does really impressive optimizations of the transformer architecture. So you can do things like you can fuse operations in the transformer to basically run faster on certain CUDA kernels. And you can do like cool things to do with like basically how you shard the model across different GPUs. So if you're doing any sort of generative text task, as far as I know today, this is like the kind of current state of the art for deployment.